Okay, we're going to try and do all of integration from year 2, which is pure year 2, chapter 11, summarized all in one video. Now, I need to state this at the beginning. This video is not going to teach you these things from scratch. This is for people who already have looked through my integration playlist, already been taught integration by their teacher. This is to kind of pull all of that together and see it all in one video, maybe perfect before doing an exam or just recapping some things. If you do not understand differentiation, you will not be able to understand what is in this video. So make sure that you're an absolute pro on differentiation. Now, that's a bit too much talk for me because I think this is going to be a long video, and the way we're going to do this, I'm not going to be teaching these skills from scratch. I have got 12 questions here and I have got 10 different techniques. This one is going to be asked about twice. This one is also going to be asked about twice, which is integration by parts and the standard result. These special cases that we have down here are going to be covered on the next slide. And then this is taken from the formula book for integration by parts. So I have these 12 questions. I'm going to go through them in order. And when I've used one of these techniques, I will tick it off so that we're in a slightly kind of better position of all of these different techniques that there are. So we've got the standard result, but it might be a variation on that. So it might be something like a function with ax plus b, a trigonometric identity, algebraic manipulation. We've got reverse chain rule with trig, reverse chain rule that is not with trig, and integration by parts. This is for expressions which are written as products. So for example, this is a product because we've got two things multiplied. This is a product because we've got two things multiplied. And then for fractions, I've kind of left the fractiony ones at the second part of these questions here. We can either split the numerator, which I'll explain when we get to it, partial fractions, algebraic division, or the reverse chain rule, where the numerator is the derivative of the denominator. So I've already done too much talking. Let's get started, and we're going to begin by having a look at the integral of sine x plus cos x all squared dx. Now, this looks like one that is definitely going to need some algebraic manipulation, first of all, but in particular, it is a trigonometric identity. So obviously I'm going to have to expand these brackets here first. Now this is going to expand to a sine squared x. You'll then get a sine x cos x, but there will be two of them. So it will be 2 sine x cos x, and you will also have a cos squared x. And now the reason this is going to be my example for trigonometric identity, meaning I can tick this one off, is because I need to know some stuff to do with identities. Now I know that the sine squared plus cos squared, that is just equal to 1. And I should know that 2 sine x cos x is just equal to the sine of 2x dx. So if I wanted to actually finish this integration off, I can say that the 1 is going to integrate to an x. And then we've just got a standard result for this part, which is that it is going to be a cos differentiates to sine, or minus cos. So it is going to be a minus cos of 2x. But because of this 2x that we have here, I'm going to also have to have a half outside the front, and of course a plus c. Now if I was to differentiate it, the x would differentiate to 1, which is what we wanted, and this minus a half cos x, well, cos goes to minus sine, so it would be the minus a half multiplied by minus sine of 2x, but there's also the 2x, so from the chain rule it gets multiplied by a 2. The negatives cancel, the half and the 2 cancels, and we get the sine 2x, which was the thing that we're looking for. So the reason I did that differentiation in red there is to remind you that you can and probably should differentiate your answers to check that you have done the integration correctly. Okay, this second one that we've got, we're going to be integrating 5 sec 3x tan 3x. Now have a look down that list and think which of these it's going to be. Well, it looks like it could be a product where maybe this is the derivative of this. Nope, I don't think that's going to be working for this one. This is just a standard result where instead of there being an x, there is a 3x. Now you should know, and this is in the formula book, but I asked people to memorize it from the differentiation chapter. We should know that the derivative of sec x is sec x tan x. So we should be able to integrate sec x tan x back to sec x. So this is definitely going to integrate back to a sec 3x. There is a 5 that was already there before, but remember if you were to differentiate this, you would have the extra 3, so we needed to counter that by dividing by 3, and then again there is a plus c that we have got here. Now, I probably should have said this at the beginning. When you think about integration, it is used to be called anti-differentiation. So we're always trying to think what differentiated to give me this answer. So I should tick off the fact that this was a standard result, just one of the standard things we should know. Now, our next one we've got here is a product. We've got an x multiplied by a sine of 2x. It's not reverse chain rule, trig or non-trig, because x is not the derivative of sine 2x. This looks like it's going to be a great example for doing some integration by parts. So we're going to be integrating x sine x, and I would say pretty much all the time, apart from our special case that we have here, you'll take the algebraic part, meaning the x part, as the thing that you're going to use for u. And we're talking about u from this u dv by dx that we have here. Now, when I do integration by parts, I would write down that u is the x part, and then they have it here as dv by dx. I just write it down as v dash, and I write it down a little bit lower, because in a moment, when I go down from u, I'm going to go x to 1 by differentiating. And when I go up, I'm going to go from v dash to v by integrating. When you integrate sine x, you get minus cos x, because cos differentiates to minus sine, so minus cos will differentiate to sine x. Now, using the formula, you can either use the formula book, but I do this very visually here. You can see that we have already used the u dv dx, this u v dash. Now, for the next part, what we're going to have here, we have the uv, which is this part, which comes from this bit. And that uv is a minus x cos x. And then our last part is to subtract the integral of minus cos x times by 1 dx. Now, because there's a negative there and outside the front, I can change that to a positive so that it gets written like this. And the reason I kind of draw it in this way is because you find for integration by parts, you have that first diagonal, and then you get the top part of this bit and then the next bit. And for me, I don't know why, I always say this looks like a picnic bench from the side, or like a table from the side. So you get that crisscross pattern, but without that part along the bottom. So all that's left to do is actually finish off by integrating cos x, and the derivative of, the integral of cos x is sine x, and of course we get a plus c there for this question. If you wanted to, you could differentiate this and see that it does go back to x sine x. So we've ticked off that integration by parts. Now, my next one that I've got here, I've got e to the x plus 4 all squared. Well, it kind of reminds me of this first one. I need to do some manipulation first of all. There's not going to be a trig identity. I think this one is going to be our algebraic manipulation. I wonder if I'll be able to squeeze it on this page here. So what's that? E to the x plus 4 all squared. I probably should have added, you could probably do all these questions yourself first and then see, using that checklist, whether you've got them right. And that checklist is there to kind of help us. So e to the x times e to the x, when we expand these double brackets, is e to the 2x. You then get a 4 times e to the x and another 4 times e to the x, which is 8e to the x. And you get the 4 times 4, which is 16. And this we can all integrate now. So we know that e to the 2x just integrates to itself, but we have to counter the fact that there's the 2x here. So we have to have the half. 8e to the x, very easy, is just going to integrate to itself. 16 goes to 16x, and then we have the plus c. So I'm not going to do all the details of this teaching. You should know how to do some of the basic bits of integration. This is really just a quick summary of this. So this one that we have here, we have a 2x and a square root of x plus 2 in this case. Now, there's a lot of different ways you could do this. You will notice I have not mentioned substitution anywhere here. Substitution can be used in this particular one, but I've got substitution being covered later on down here. Okay, so I'm going to see if I can show you this away without using substitution. And again, I have a product of two things. Now, it's not going to be a reverse chain rule because 2x is not the derivative of this second function, which is the x plus 2. So I'm actually going to use another example of integration by parts for this one. So for this question, it is x multiplied by the square root of x, it was 2x multiplied by the square root of x plus 2. So I'm going to write that in its index form. And I've already told you about integration by parts, so I can go a little bit faster. Now, I am going to use this as my u in this case. So I'm going to say that u is 2x, and that the v dash we have here is x plus 2 to the power of a half. So when I differentiate that, I get 2. When I integrate this, I'm going to have x plus 2. I'm going to increase the power to 3 over 2. This is like a standard result. And then I will also divide by that new power, so I get 2 over 3. And because the derivative of x plus 2 is just 1, there's nothing else I need to change about this. It's quite a simple bit of integration. So we have already used the first diagonal that came from the question, we're now going to say we get the uv, so we have the 2x times 2/3, well that is going to be 4/3 x plus 2 to the power of 3 over 2, and then we are going to be subtracting the integral of these two things multiplied, which is 4/3 x plus 2 to the power of 3 over 2 dx. So continuing with this, you get 4/3 x plus 2 to the 3 over 2, and then here I'm going to increase the power on the x plus 2, so it's going to go to 5 over 2, and then I'm going to have the 4 over 3 that's still there from before, and you're going to multiply it by the reciprocal of that, like you normally do with integration. You increase the power by 1, and then you either multiply by the reciprocal or divide by that new power. So it's going to be the 2/5 there plus c. So just a little bit of extra simplifying. That's 4/3 x plus 2 to the power of 3 over 2 minus 8 over 15 x plus 2 to the 5 over 2 plus c. Now, it's possible you do this with a different technique and you don't end up with exactly the same thing. If you don't end up with exactly the same thing, it's possible that it could still be the same function. So you might want to type it into like Desmos or to some graphing software. And if it's exactly the same graph, then you know that it's identical. I also have got another video where I kind of explain all of the different thinking about how I approach this. So I will also link that in the description. It's like how to integrate anything in A-level maths. And so if you want more practice on that, that is a really, really, well, I'm saying it about my own video, but it's a really good video that kind of describes how I think about some of this stuff. So we've done 5 of the questions. The next one is 3 cos x sine squared x. So I am doing 3 cos x sine squared x dx. Now, if you don't know how to do differentiation, you will never be able to understand this next one. This is looking at a product, two things being multiplied. I think it has to be then the reverse chain rule with trigonometry for this one. So we're saying to ourselves something differentiated to give us this thing. And it looks like this cos x is the derivative of the sine x that we've got there. In fact, if I write it in this kind of form, that 3 cos x is then multiplied by sine x all squared, if you're really good at differentiation, you will think to yourself, oh, I've differentiated something that looks like this before. And in fact, it looks like it is going to be something to do with sine x all cubed, because we know that when you differentiate sine x all cubed, you pull the power down, you reduce the power by 1, and then you multiply by the derivative of this inside part from the chain rule, which is cos x. And actually, that's exactly the thing that we wanted it to differentiate to. So there's nothing that even needs to be adjusted about this particular question. Don't know why I've got the integration sign there, because we actually have done the integration. And so that is going to be our final answer. It's just sine cubed x plus c. So always differentiating your answer is going to be a good way of doing this. There was no scaling that was required for this one. Scaling meaning you might have needed to put a number outside the front. But because we had the 3, we were good to go. So that was our reverse chain rule with trigonometry. Very, very popular kind of topic. And we're now on to this one. So we have 4x, x squared minus 4, all cubed. 4x, x squared minus 4, all cubed, integrating with respect to x. So we have got a product of two things, which makes me think it's got to be this reverse chain rule of non-trig. But we're going to try and explain why this is a reverse chain rule. Well, we've got this thing that is all cubed, and luckily outside the front, we have got 4x. Now, the derivative of this thing that is being cubed is 2x. So that's related to 4x. Let me just go in and actually start the answer for this. I think this dominant function that we've got here, this x squared minus 4 all cubed, I think that came from an x squared minus 4 to the power of 4 being differentiated, because that power of 4 would come down. Don't worry about that too much. We would reduce the power by 1 to get the 3, and we would be multiplying by the derivative of this, which is 2x. So crucially, we're getting that x outside the front, which is important. So what I'm going to do is I'm going to differentiate this, and then I'm going to use that to help me to decide what scaling I should have outside the front. So I'm going to pull the power down. I'm going to reduce the power by 1, and I'm also going to multiply by the derivative of this thing I've underlined, which is 2x. So it looks like I have 8x, x squared minus 4 cubed, but I don't want it to be 8x. I want it to be 4x, which means I need to scale it by putting on an extra half outside the front. Because if there was an extra half at the front, there'd be a half here, there'd be a half here, and we would correctly end up with the thing we were trying to integrate in the first place, which was this. So I'm actually going to keep some of that working because I think that working is probably useful for us in this question. So I'm going to just whack this up here and put this with a plus C. Okay, so have I ticked that one off? Reverse chain rule, non-trig. We are now coming to our last few. So we've got the fractional ones here that are either going to be these four, and one of them is a standard result. So we have 4 over 2x minus 1 cubed. Now, sometimes when people see this, 4 over 2x minus 1 cubed, as soon as people see a fraction like this, they go, oh, it's ln, it has to be ln. Well, this one isn't going to be an ln because of the fact that we have a cubed here. If it was by itself and there was no cubed, it was just 2x minus 1, it would be ln. But it's not always going to be ln. Now what I'm going to do is I'm going to rewrite this. I'm going to write this as 4 brackets 2x minus 1 to the minus 3. This just looks like a standard result to me. This just looks like a standard result. So I know what kind of thing this is going to integrate. It's going to be something with a power of minus 2, isn't it? And this is fine because the derivative of this 2x minus 1 is just a constant, whereas in this previous one, it was a variable that had an x with it. So let's do the same thing we did. I'm going to practice differentiate it in red. So I'm going to pull the power down. I'm going to reduce the power by 1, and I'm also going to multiply by the derivative of this, which is a 2. So it currently gives us minus 4, 2x minus 1 to the minus 3. But I don't want it to be minus 4, 2x minus 1 to the minus 3. I want it to just have a 4. So I needed to counter that by having an extra negative outside the front, which makes it turn to this thing, plus c. And of course, if you wanted to, you could write this as minus 1 over 2x minus 1 all squared. So that was just a standard result. Did I tick that one off yet? No. So we're now on to these final 4 fractions here. And we've got these 4 different techniques to split the numerator, which is kind of just year 1 technique, really. Partial fractions, algebraic division, which is when we have a top-heavy fraction. That's when you want to do algebraic division. And then the reverse chain rule, where the numerator is the derivative of the denominator. Now, I suppose I did say something there that might be quite important to help us think about this one. This one, I think, out of these, I can't split the numerator very effectively because I have 2 terms, a binomial in the denominator. You can only split the numerator when the denominator is just a single term. Well, you can split it when it's a binomial, but it's just not as effective. Okay, it doesn't look like partial fractions because we've only got one thing in the denominator. I think it's going to be algebraic division because it is a top-heavy fraction. So I'm going to do 2x squared minus 3x plus 1 divided by 2x squared minus 3x plus 1 divided by x plus 2. Let me double check I've done that right before I then start doing everything incorrect. So I'm going to do the algebraic division for this question. So this is 2x squared minus 3x plus 1. I'm going to divide it by an x plus 2. So I'll concentrate. I'll do the 2x squared divided by x. That is just 2x. And then I'll multiply the 2x by the x plus 2. So that's the 2x squared plus 4x. Now when I subtract, these cancelled, that was the whole point. Minus 3 minus 4x is minus 7x, and I'll pull that minus 1 down. So I now have the minus 7x divided by x, that is just minus 7. And when I multiply this by minus 7, I get the minus 7x, and I get the minus 14. Luckily, these cancel, that's the whole point. And I get 1 minus minus 14, which is 15. So this is the same thing as integrating this part, which is just a 2x and a minus 7. And then there is also a remainder of 15, which is still being divided by the x plus 2. Let me write that a little bit better. We've got that remainder of 15, which is still being divided by the x plus 2 dx. So the 2x is just going to integrate to x squared. That's like year 1. The minus 7 goes to minus 7x, and this is a standard result. We know that when you have something over x plus 2, it is just going to be a 15 ln of x plus 2, because we know when you differentiate an ln function, you get 1 over that function. I'm just leaving that 15 outside the front, plus c. So that was an example of us doing algebraic division. Now you'll notice I haven't listed all of the things that everything integrates to. If you know what everything differentiates to, you should know what everything integrates to. And this is going to be a long enough video to begin with anyway. So this, this you should be screaming out for this one. This is a typical example of partial fractions. So we have a 10x minus 2 over some stuff that we've got there. So I'm just going to quickly box that part off so I have a bit more space. So I'm doing the integral of 10x minus 2 all over 2x plus 1 and x minus 3. 2x plus 1 and x minus 3 with respect to x. So I'm going to do a quick bit of partial fractions. 10x minus 2 over 2x plus 1, x minus 3. This is going to be my a over 2x plus 1 and my b over x minus 3. So 10x minus 2 is a times by x minus 3 and b times by 2x plus 1. So I'm going to start off by letting x equal 3. Now, if x was equal to 3, the left-hand side would be 30 minus 2, which is 28. And this would be cancelled. 2 times 3 plus 1 is 7. And we get 7b. So b is equal to 4. Now, if x was equal to minus a half, that's to get rid of this part. That would be 10 times by minus a half minus 2. That's minus 7 on the left-hand side. And if it is minus a half, that would be minus a half minus 3. That is going to be minus 7 over 2a. So I shall do minus 7 divided by minus 7 over 2. That just means that a is equal to 2. So I can now actually continue doing the integration because I've got it written in its partial fraction form. It is going to be a 2 over 2x plus 1. That's my a over 2x plus 1. And my b, which is 4 over x minus 3 dx. Now these are going to be ln ones when we integrate these. So this is going to be an ln of 2x plus 1. I don't need anything outside the front because the derivative of this is 2, which we already have there, so I can just leave that one. And then this one is going to be an ln of x minus 3, but I do need the 4 because without the 4, it would just have a 1 outside the front because the derivative of this is just 1. Now, if this is all sounding like complete gobbledygook, you definitely need to just go and do some practice on this yourself. You're not going to be able to learn this just from this video. This is really to kind of refresh you and make sure you're kind of on track with things. So we've now got final two. We've either got reverse chain rule or split the numerator. Now, I think this is going to be the split the numerator because there's this single term here. So we need to try and figure out why this is reverse chain rule. This is 6x squared minus 4. 6x squared minus 4 over x cubed minus 2x. Okay, now this is where you have to be really good at spotting this. It looks to me like the derivative of this is 3x squared minus 2. Let me just jot that down. 3x squared minus 2. Oh, look, this thing and this thing are related to each other. This is double the derivative of this. So this is telling me it is going to be an ln function. If it is ln of x cubed minus 2x, we know that when you differentiate this, you get 1 over x cubed minus 2x multiplied by the derivative of this, which is 3x squared minus 2. In other words, it just differentiates to this. So the only difference is we don't want it to be 3x squared minus 2. We want it to be 6x squared minus 4, which means we need the whole thing multiplied by a 2. So we're going to put the 2 outside the front of it like this. Okay, very, very tricky question to spot these kinds of things. But the more you do of this, the more you will get used to it. And of course, we have plus c. So I can tick off there from our checklist. We did the reverse chain rule. We are now going to have a look at splitting the numerator for this final question that we have right here. Rather than me scrolling back up and down, I can just keep it on my computer screen so I can have a look at it. So we're going to be integrating x minus 2, x minus 4, all over 4 root x, which of course I'm going to write in this form. So a little bit of algebraic manipulation first. The numerator expands to an x squared minus 6x plus 8. And this is all being divided by 4x to the half. Now you could have done this in year 1. Splitting the numerator literally means this. It means let's write it as an x squared over 4x to the half minus 6x over 4x to the half plus 8 over 4x to the half. Now you can obviously only split fractions in this way by splitting the numerator. You can't split a denominator. You can't have like 2 over x plus 3. This is not the same as 2 over x plus 2 over 3. We know that, okay? You can only do this with the numerator. So just a little bit of simplification. I'm going to say that this is going to be, well, the 4 is in the denominator, so there's a quarter. X squared and x to the half will leave me with x to the 3 over 2. 6 over 4, that's 3 over 2. and this is x to the power of 1, isn't it? So it's going to be an x to the power of a half. 8 over 4 is 2, and that x is in the denominator, so it's going to have a negative power, and that's dx. So let's just do some basic integration here. So that's 5 over 2. Well, we'll have to do a quarter multiplied by 2 over 5. So we get it's a tenth for this part. This is going to be the x to the 3 over 2. So I need to do 3 over 2 times by 2 over 3. Oh, great. That's just going to give me it as a minus, because obviously that power comes down. Oh, this is going to be a long video. And our last one, I'm going to increase that power to a half. And I'm also going to multiply 2 by the reciprocal of this, which is 4. And again, you could differentiate this to double check that it does all come close, does all differentiate back to the thing that we were looking for. Now, I hope I've put plus c everywhere. It looks like I have. If I've made any mistakes, this has been a very, very hard video to plan. Very, very hard video to plan, because I'm trying to cover absolutely everything. Now, there are a couple of special cases, which is integrating anything to do with ln x and integrating sine squareds and cos squareds. I know we had a sine squared and a cos squared here, but they combined to make a 1. So we're going to be looking at special cases where we're wanting to integrate something that looks like this or that looks like this. Okay, so special cases with ln x. Anytime we are trying to integrate a function which contains ln x, like here, here, or here, we always use integration by parts, with the logarithmic part taking priority for u. Previously, the algebraic part was taking priority for u. If there's nothing else with the ln x, like in this case, then the v dash is going to be equal to 1. Now, I'm going to do this one here. This one actually gets answered as part of this question. And this one, if you want to try it yourself, the answer is down here, so you can try it. But remember, u would be ln x. So this is the one I'm going to integrate. I'm going to do this one. I am integrating ln x all squared with respect to x. Okay, first of all, I'm going to take priority for u is going to be the ln function, which is ln x all squared, meaning that the v dash function is just 1. So I'm going to start off by differentiating. I'm going to pull that power down and reduce the power. So I get 2 ln x, but it gets multiplied by the derivative of ln x, which is 1 over x. In other words, it is 2 over x ln x. And when I integrate 1, I get x. Okay, so I've already used this branch. I'm now going to have this branch, which is x times by ln x all squared. And I'm going to have to now subtract the integral of these two things multiplied with each other. Now, the x and the over x are going to cancel, which just leaves us with 2 ln x dx. Now, to make this really clear, I'm actually going to put the 2 outside the front, so you can now see I'm actually going to be answering how to integrate ln x. Well, I'm going to do integration by parts again for this section. So u is ln x, v dash is 1, which means this is going to be x for v, and ln x differentiates to 1 over x. We have already used that branch. We're now going to have this, and then we're going to subtract the integral of this. So writing the whole thing, we still have the x ln x squared. We're going to be subtracting 2 lots of the uv part, which is the x ln x, and we're going to be subtracting the integral of this times by this. X times by 1 over x is just 1. So our final answer is x ln x squared minus 2x ln x. Well, 1 integrates to x, so this is just a minus x times by a minus 2, which is a plus 2x plus c. I think I've done that all right. Yeah, minus 2x ln x. This integrates to minus x. Minus x times minus 2 is plus 2x. And again, you could differentiate this, and it would come back to ln x all squared. So you can try this one yourself. That's going to be the u part that we have. That's going to be the v dash part, and you're going to go from there. Now, if we wanted to integrate sine squared x, these are always like right at the end of the exam paper. If you want to integrate sine squared kx or cos squared kx, we use a rearranged form of the double angle formula for cos 2x. So, cos 2x, there are 2 forms that you should know by heart. There are actually 3, but these are the 2 we're going to be using. It's either 2 cos squared x minus 1, or it is 1 minus 2 sine squared x. So if we rearrange this, we get cos 2x plus 1 is 2 cos squared x. And when I half it, I get a half plus a half cos 2x is cos squared x. And then the other one for sine, if I rearrange this, I would put the 2 sine squared x onto this side, and that is going to be a 1 minus cos 2x. When I divide by 2, I get the half minus a half cos 2x. Now, if you're doing further maths and you've looked at polar equations, you will know you have to do an awful lot of integrating of sine squared and cos squared. So I would highly recommend memorizing those two things I've just put the little box around. It is not possible to just integrate sine squared x by raising the power and dividing by the power, because it's not going to have the cos x in front of it that we need. We have to use this technique. So looking at the bit that's in the right hand side that's highlighted in yellow, I'm actually just integrating a half minus a half cos 2x dx. So a half integrates to a half x. Sine goes to cos, so it's going to be a sine 2x, and there's going to be a minus a quarter plus c. Yeah, sine goes to minus, yeah, that's all correct for this. So the integral, not very pretty looking, but the integral of sine squared is this part. And the key thing to notice in this formula is when you have the squared part, the angle doubles from the x to the 2x for this bit. Okay. So this one, there are other approaches to doing this one. I'm just going to go straight in with using the formula for both of these. If you wanted to do the other approach, you could say to yourself, oh, I know that this is sine x cos x all squared. I know that sine x cos x is a half sine 2x all squared. So it's a quarter sine squared 2x. You are going to end up with exactly the same point that we do by using my technique that we've got. So there are multiple approaches. You're going to end up with the same thing. So sine squared x, cos squared x. Can't do reverse chain rule because this is not the derivative of this, or vice versa. Sine squared is a half minus a half cos 2x. Cos squared is a half plus a half cos 2x dx. Expanding these brackets, a half times a half is a quarter. And then I'm going to have these two multiplied, which is a quarter 2x. And then these two multiplied, which is minus a quarter cos 2x. So they cancel out. It's like a difference of 2 squares. And I then get minus a quarter cos squared 2x dx. Now I've got another cos squared in here. So I'm going to use that identity again. This is minus a quarter. We know that cos squared is a half plus a half cos of, well, previously it was cos of 2x, right? We said that cos squared x was this, but the x went to 2x. So the 2x is going to double to a 4x like this. Super hard question. I'm wanting to have the hardest things that you can come across here. So that is a quarter minus a quarter times a half. That's a quarter minus an eighth. Oh, that's just an eighth. So let's save me a line. I'm going to write that as an eighth. And then I get minus 1/8 cos 4x dx. Super challenging question. Okay, this is meant to be hard. It's one of the hardest parts of A-level maths. So I get an eighth x. I know it's going to be a sine 4x because sine differentiates to cos. And I'm going to have to also counter that eighth with the 4 that's in front of the x. So I get 1/32 sine 4x plus c. Now I think that technique that I did over here, I think if you did it that way, you might end up with something that looks slightly different to this, but it is still equivalent to it. Wow, oh my god, this video is going to be so long, but we're going to do it. We're going to do it. Hopefully in one recording as well. So in all these techniques up here, I didn't mention substitution. Now your teacher might do a lot of substitution with you. That might be the technique you use a lot of. Substitution is a very powerful one, but there's quite a lot of steps and it's quite easy to make a mistake. So they often tell you what the substitution is, okay? Let's go straight in with this. So I've said, of course, there is another very powerful tool for substitution. Convert the easy part using the given substitution. Often the substitution is going to be the denominator because the denominators are the annoying thing that we have to work with in integration. You can often leave some things in x. We'll see it down here. They might cancel with something later. Don't forget to do the substitution for dx. And remember, if there are limits, you do need to change the limits so that at the moment these limits are for x. We need to make sure that the limits will be matching for u at the end. Okay, well, the denominator is super easy. The denominator is just going to be u. The numerator, though, I need to find out what x is equal to. So if I do u minus 1, that would give me the square root of x. So if I square it, I get what x is equal to. So the numerator is u minus 1 all squared. And if I just do a bit of differentiation here, if I do du by dx, du by dx, is that the way I want to do this? Yeah, I think so. Du by dx, if I differentiate this thing that we have, well, that is x to the half, right? That is going to be a half x to the minus a half. So rearranging this, this is that du dx is 1 over 2 the square root of x. It's 2 over the square root of x here. So let's try and make dx the subject. I'm going to multiply up by the 2 root x du, and then I'll multiply up by the dx like this. So I actually know what root x is as well. The square root of x is u minus 1. So I have 2 multiplied by u minus 1 du is equal to dx. So this is the du part. Excuse me, the dx is 2 u minus 1 du. I'm wondering if there was a quicker way I could have done this, actually. Let me just have a quick moment to think. Could I have just differentiated it with x as the subject? I think I probably could have done that even easier. Let me just quickly check this. So if I had this version, that x is equal to u minus 1 squared, I don't think this is going to be any better. Dx du is 2u minus 1. Yeah, so it's the same thing. 2, yeah, gives you the exact same thing. Maybe it's easier, maybe it's not, whichever way you wanted to try it. Okay, we better keep going, So we haven't changed the limits yet. When x is 0, let's find out what u will be. So when x is 0, u is the square root of 0 plus 1, which is just 1. And when x is 25, u is the square root of x plus 1, which is 5 plus 1, which is 6. So I actually can start doing a bit of algebraic manipulation in this particular question. It's not going to be particularly fun, but this is going to be the integral from 1 to 6. Well, u minus 1 squared, we've actually got u minus 1 cubed now. So we have 2 lots of u minus 1 cubed all over u du. If you want to, you could put the 2 outside the front, which I probably will do. Now, u minus 1 cubed, you can do either binomial expansion or you can slowly expand it. It's going to be u cubed minus 3u squared plus 3u minus 1, all divided by u du. And then I'm going to have to split the numerator. So each of these things I want to divide by u. That's going to be u squared minus 3u plus 3 minus, not minus ln, I'm jumping ahead of myself, minus 1 over u du. Let's go over here. So I'm still going to have the 2. I can actually do the integration now. So the u squared will be a third u cubed. It is then going to be 3 over 2u squared plus 3u minus ln u. And that is all between, I've started dropping my limits between 1 and 6. Now you do need to show this process. I'm going to sub in the 6, so that's a third times by 6 cubed, minus 3 over 2 times by 6 squared, plus 3 times by 6 minus ln 6. And then subbing in 1, that's just going to be a third, minus 3 over 2, plus 3. And then ln 1 is just 0. So I'm not even going to need that part. Okay, all on my calculator. Let's see how this goes. So that is going to be, I'll do the 2 at the end. I'm going to have 6 cubed divided by 3 minus 3 over 2 times by 6 squared plus 3 times 6. So this is 2 lots of 36 minus ln 6. And then I'm also going to have to subtract these. I'll tell you what, I'll just do that straight from the 36. So I'll do 36 minus a third, plus 3 over 2, because of the minus and the minus, minus the 3, and we get 205 over 6, minus ln 6. So multiplying everything by 2, that is 205 over 3, minus 2 ln 6. What I would probably do is then put that in my calculator, put this original thing in my calculator to check that I've got it right. And I'm actually probably going to do that while we have a look at this next one, which is a complicated trig kind of one. Now, I'll tell you what, I'll do it at the end, because if I've got it wrong, I'm going to have to re-record this whole video. So let's keep going. Let's do the substitution. They've told us that u is 1 plus sine x. That makes this part super easy. So we have got the 1 plus sine x is just going to be my u squared. And then if I find out what sine x is equal to, that is just u minus 1. So sine x is just u minus 1. Well, that's nice and easy. This cos x doesn't feel like an easy one. So I'll tell you what, I'm going to leave it, and it might cancel out with something in just a second. Now, if I differentiate this, I get that du dx, sine 1 goes to nothing and sine x goes to cos x. So rearranging, du will get divided by cos x, the cos x comes down and the dx comes up. And we get the du over cos x. So actually not finding out what cos x was really helpful. I suggested that up here because the cos x is going to cancel with that part there and we don't need to worry about it. So we do just need to change the limits. When x is equal to 0, u is 1 plus sine of 0, which is just 1. When x is pi over 2, the upper limit, u is 1 plus the sine of pi over 2. Sine of pi over 2 is sine of 90, which is 1. So 1 plus 1 is 2. So this one's a lot easier than the one that we had at the top. It is just the integral of u minus 1 u squared du between 1 and 2. So when I expand these brackets, that is u cubed minus u squared between 1 and 2. Let's go straight in with the integration. That is a quarter u to the 4 minus a third u cubed between 2 and 1. So it's a quarter 2 to the 4 minus a third 2 cubed. And then when you sub in 1, we don't even need to show that. It's just going to be minus a quarter minus a third. So on my calculator, 2 to the power of 4 divided by 4 minus 2 cubed divided by 3 minus a quarter plus a third, and I get the final answer of 17 over 12. And again, I would take this original thing that I've got written, I'd type it in my calculator and see if it gives me that answer. Wow. I wonder how far through this we are. Okay, let's keep going. So parametric integration now. I did say parametrics we would cover throughout the differentiation and integration bits, and here we are. So for Cartesian, this is what we normally do. We normally do y dx between a and b. So for parametric, we still do a y dx, but because y is in terms of t, we can't do it with respect to t. So if we want to do it with respect to t, we need to add in a dt here and here because we want it to be integrated with respect to t, but then we can make these things effectively cancel out. And if they cancel out, we're then in a position to kind of integrate like this. And of course, these limits are now going to have to change to t1 and t2 like this. Okay, so this is how we do parametric integration. The curve shown in the diagram has these parametric equations. X is 2 cos 2t and y is 3 sin t. And this is for t between 0 and pi over 2. The region R, shown in the diagram, is bounded by the curve, the x-axis, and the line x equals minus 2. Find the exact area of R. So in this question, the area of R is going to be the integral of y dx dt, dt. Now, previously, if we were going to do this, it looks like the limits are going to be, you have this minus 2 part, you would do that as your lower limit, and then whatever this part here is as your upper limit. So I want to find out what the t values are that correspond to this. So when x is equal to minus 2, let's find out what t is equal to. So when x equals minus 2, you might guess that it's going to be that t is 0 over here, but it might not be. So when x is minus 2, I'm going to use the parametric. I get that minus 2 is 2 cos 2t. So minus 1 is cos 2t. If you do the inverse cos of minus 1, that's going to tell us that 2t is equal to pi. And so t is pi over 2. So interestingly over here, t is equal to pi over 2. And if you were to work out over here, you'll see that t is equal to 0 because this is when y is equal to 0. And when y is equal to 0, we get that 0 is equal to 3 sin t. and you'll see very quickly that t is equal to 0. So because we're going from left to right, we're actually going to put down here, the lower limit is pi over 2 and the upper limit is 0, which seems really strange because we normally have the bigger limit on the top. But I'll look at this exam tip in just a second to help us to deal with this. Okay, so need to differentiate the x to get dx dt. Well, this is going to differentiate to, cos goes to minus sine, so it's going to be a minus sine 2t. There's a 2 times by the derivative of this 2t, so it's going to be a minus 4 sine 2t. So this means that r is the integral from pi over 2 to 0 of y, which is 3 sine t, multiplied by minus 4 sine 2t dt. And this is where the exam tip comes in. If you flip the limits, so we have them the traditional kind of way around, you can just simply negate the integral. There's this negative here. If you get rid of that negative, you can just flip the limits. So I'll tell you what, I'll keep going with this question down here. And you get the limits back to our normal direction for this, so that we have the 0 and the pi over 2. I'm going to get rid of the negative, and this 3 times 4 is a 12, which can go outside the front, leaving us inside with sine t sine 2t. Now this needs a bit of trigonometric manipulation. So you should memorize that sine 2t is 2 sine t cos t dt. Let's keep that 12 there. So we have a 2 sine squared t cos t. I'll tell you what, it might be even more helpful if I write it this way around. If I write it as cos t sine squared t dt, you might have a go at thinking of what this is going to be. So this is a reverse chain rule, because this dominant function, the sine squared t, when you increase that power to cubed, and if you're going to differentiate it, you would get a cos t that comes from it. Tell you what, I'll get rid of that 2 and put it outside the front. So I have it as a 24, 0 to pi over 2, cos t sine squared t dt. Let's go up here. So r, if we keep going, is 24, and I think it's going to be something to do with sine cubed t. If you were to differentiate sine cubed t, this is red for differentiation, you would pull the power down, you would reduce the power by 1, and you would multiply by the derivative of sine, which is cos t. So actually, it's almost the thing that we wanted, apart from ours has a 3, this one doesn't, so we have to counter it by adding in an extra third outside the front. Now, if you really want to, you could take that third and put it with the 24 so that we just get an 8, but you don't have to do any of those stages. If you want, you could just evaluate it with these limits. And we didn't need to change the limits in this question because it was already the t limits that we'd got. So r is 8 times by the sine cubed of pi over 2 minus sine cubed of 0. Well, sine of pi over 2 is just 1, so it is just going to be 8 times by 1 minus 0. So the area is just 8 for this particular question. And again, I'm going to double check this, that I've done all of this multiplication correctly. I think I have done. Oh no, I said I had to have a third. No, I did do it. I did do it. So the area, it feels very bizarre that we have the area is exactly 8. Okay, I just took a quick break. I was so thirsty, and this is telling me how long this video is going to be. Let's keep going, though, with differential equations. So when you have differential equations, there is always going to be part of it where you need to separate the variables to do some integration. So here, if we had that dy by dx was some function of x multiplied by some function of y, you want to keep all the y stuff on the left and keep all the x stuff on the right, meaning we would get this g of y over to the left-hand side by dividing it, 1 over g of y, and there'd still be the dy over dx. But what I would also do is I would take that dx, I would send it to the right by multiplication so that we get this, and then you just put the integration signs on both sides of it like this, okay? And then I promise after differential equations, it is much easier on the last slide. So the population of a colony of rabbits in hundreds of thousands measured t years after the 1st of January 2010 is modelled by this differential equation, dp dt equals p over 1 minus p. The population of rabbits on the 1st of January 2010 is 30,000. So immediately I'm going to say here, when t is equal to 0, the population is 0.3, 30,000 out of 100,000. we're going to solve the differential equation to show that the population is equal to this thing. So we have it dp dt. I'm going to get all of the p stuff onto the left-hand side. Well, I can only get it over there by division, so it's going to be 1 over p, 1 minus p, dp dt is just equal to a 1. That's from dividing the p, 1 minus p. So if I put the dt onto the right-hand side, I get 1 dt, and I get 1 over p, 1 minus p, dp, and then I just put the integration signs in front of it. So the right-hand side is going to be really easy. It's just going to be a t plus c, but I'll come to that in just a second, because to integrate the left-hand side, I, of course, need to do partial fractions. So 1 over p, 1 minus p, is going to be an a over p plus b over 1 minus p. So that's a 1 minus p plus bp. Well, if p is equal to 1, then we get that 1 equals b, and if p is equal to 0, then 1 is equal to a. Oh, nice and easy. We just get 1 over p plus 1 over 1 minus p dp is equal to the integral of 1 dt. You don't even actually need to have that 1 there. You could just write it like this. It's equivalent, okay? So when I do the integration, 1 over p integrates to ln of p. This would be the ln of 1 minus p, but because this would differentiate to a minus 1 and I want it to be a plus 1, I will have a negative in there, and 1 integrates to a t plus c. Now we don't want the c, we need to actually find out what the c is equal to. So I'm going to use this information, that when t is 0, p is 0.3. When t is 0, p is 0.3. So this is the ln of 0.3 minus the ln of 1 minus 0.3 is equal to 0 plus c. So c is, remember with ln's, you can do them as like a division. That's the ln of 0.3 over 0.7, which is the same as the ln of 3/7. So let's go up here and hope we can get this all in one question. We're now going to try and find out what p is to make it look like this. So we have that ln of p minus ln of 1 minus p is equal to t plus c, which is the ln of 3/7. Now I think we can probably combine all of this stuff using some log laws, right? So ln of p minus ln of 1 over p, that's just going to p over 1 minus p. And I'm subtracting an ln of 3/7 is equal to t. Now subtracting ln of 3/7, that means dividing this by 3/7, which is the same thing as multiplying it by 7 over 3. So it's 7 over 3, p 1 minus p is equal to t. So let's get rid of the ln by now writing it as exponentials. So that's 7 over 3, p over 1 minus p equals e to the t. So p over 1 minus p is going to be 3 over 7 e to the t. So a little bit of more rearranging. That's 3 over 7 e to the t multiplied by 1 minus p. Trying to make p the subject here. That's 3 over 7 e to the t minus 3 over 7p e to the t. Let's get the p's onto one side. P plus 3/7 p e to the t is 3/7 e to the t. Factorize out 1 plus 3/7 e to the t equals 3/7 e to the t. So p is 3/7 e to the t over 1 plus 3/7 e to the t. Well, what do they want it to look like? We want it to have 3 here and e to the minus t here. Okay, well I can just times everything by 7. If I times this by 7, I'm going to get 3e to the t over 7. Just going to have it on my computer screen so I don't have to keep going back and forth. 7 plus 3e to the t. And then if I want to get it as an e to the minus t somewhere with the 7, I'm going to multiply the top and bottom by e to the minus t. So if I multiply it by e to the minus t, and I'll see if I can squeeze this all in one line. Now let's multiply it by e to the minus t. The numerator is just going to be 3. These two, the e to the t and the e to minus t, is just going to cancel. And then I have the 7 e to the minus t, which was the thing they wanted us to prove. Wow. Let's get rid of this arrow so I can hopefully create myself some more space on this rather chaotic looking page, and I'll still say this is going up here. So that was all part A of the question. Now I'll squeeze in part B over here. It says determine the limit to the population of the number of rabbits. So we have that the population is 3 over 3 plus 7 e to the minus t. As t gets to a really big value, e to the minus t we know goes to 0, which means the population is just going to go to 3 over 3 plus 0, which is just equivalent to 1. So the limit is 1, which we know is 100,000 rabbits. Part C of the question says, find in which month the population of the rabbits reaches half its population limit. So half its population limit is going to be 50,000 rabbits, which is 0.5. So we're going to say that P is equal to 0.5, and we're just going to make it equal to the equation that we had. So multiplying up, a half times by 3 plus 7 e to the minus t, that's going to be 1.5 plus 3.5 e to the minus t equals 3. So this is going to be making e to the minus t the subject. I will do 3 minus 1.5, which is 1.5, divided by 3.5, that is 3/7. So I'm going to do that minus t is the ln of 3/7. So t is minus ln 3 over 7 minus ln of 3 over 7, which is that t is 0.847 years. But the question says in which month it reaches half its population limit. So I'm going to still need to create myself some extra space. Let's do it up here, and I'll just draw a line down like this. So this many years, I'm going to convert that into months. So I'm going to say in months, it is 0.847 times by 12, which is 10.16 months. Now this is the part that's kind of tricky to spot, but we're going to do it. We need to find out in what month that takes place. So if it was 1 month, let's say that it was equal to 1 instead of 10 months, it's 1 month. 1 month later would be the 1st of February, so it would be taking place in February. 2 months later would be in March. 3 months later would be in April. So 10 months later isn't going to be October, it's actually going to be in November, because it is that 1 month advanced from it. So this is going to be in November 2010, okay, because it is 10 months later. 10 months later, 1 month later is February, 0 months later is January. So it's a very, very confusing way, but it's definitely November 2010. We are so nearly there. We need to do the trapezium rule and our super easy one to finish up with as a limit of a sum. Now the formula for the trapezium rule is given in the formula book. Let's dive straight in. It says the table shows, corresponding values for x and y for y equals 2 to the power of x squared. The values of y are given to 2 decimal places as appropriate. Using the trapezium rule with all the values of y in the table, find an estimate for this integral. So between 0 and 1.5 of 2x squared dx, the estimate of this using the trapezium rule, we'll try and explain what this is. It is a half multiplied by the height. The height is the gap between these, which is 0.3. We then have y0 and yn. That is the first one and the last one. So that is 1 plus 4.76. And then we have 2 lots of the middle ones that have not been used. So that's 2 lots of 1.06 plus 1.28 plus 1.75 plus 2.71. Close that bracket and close another bracket. Get it all on the calculator as soon as we can. So 0.15 brackets 1 plus 4.76 plus 2 brackets 1.06 plus 1.28 plus 1.75 plus 2.71. Double close those brackets and I have 2.904. Using the graph, explain whether it's an underestimate or an overestimate. Well, if you look, the graph, if we were going to split it into all of these pieces, the graph is convex. So when we do our trapeziums, the trapeziums are going to be coming slightly above it. It's probably the clearest if I was going to do it with just fewer intervals. If I was just doing it with 2 intervals, you can see it would be an overestimate. But with all of the intervals we've got, maybe I could draw it a little bit more neatly. You should tell that our lines for our trapeziums are always going to go above the graph. So I'm going to say, explain whether it's an underestimate or an overestimate. I'm going to say it is an overestimate as the curve is convex. So the trapeziums, or the plural of trapeziums, is sometimes written as trapezia. So the trapezia are larger than the area under the curve. And then they like doing these questions where you then have to use the estimation to try and answer something slightly different. So we need to try and now find between 0 and 1.5 of 2x, 2 to the power of x squared plus 3. Well, I still need to make it look like the original thing. So I'm going to use my knowledge of indices. This is 2 to the power of x squared multiplied by 2 to the power of 3 between 0 and 1.5. 2 to the power of 3 is just 8. So it is 8 multiplied by 0.15 times by 2 to the power of x squared dx, which is just 8 times by 2.904 times it by 8, which is 23.232 for our estimate. And our final thing, as a limit of a sum, if you ever see something that looks like this, it literally just means integrate this thing with a and b as the limits. I cannot believe I've made it to the end of this video, and with only one break. So, as a limit of a sum, this is the sigma notation. We're going to do it as the integral sigma between 3 and 6. We are integrating x squared with respect to x. Super simple, because it's a third x cubed between 3 and 6. So what's that going to be? A third times 6 cubed minus a third times 3 cubed. Oh my god, I can't believe it's nearly finished. So 6 cubed divided by 3 minus this is 63. Don't forget this. This is something that people often can kind of forget to learn, that you can write it in this way. Now, this is everything to do with integration. If you want to go in a little bit deeper, you can obviously look at my full playlist on integration, or of course, I'm going to link in the video description my video that's about how to integrate anything. Give you a lot more input around my thinking that goes through this kind of stuff. I have been dreading making this video because I knew it was going to be very, very hard to plan, and it was even longer to film. Well, if you've got to the end of this, then that's brilliant news. Well done, well done, well done. Good luck with your revision, guys, and I hope to see you in another video soon.